This video is going to show you how to go from pH to calculate Ka. So if I read the equation, I see I've got a 0.1 molar solution of formic acid. Formic acid is a weak acid, and I know that because it is not one of our strong acids, but then also this COOH group shows me that this is a carboxylic acid, so it's an organic acid. Tells us that the pH is 2.38, and we're supposed to calculate Ka. So you can start a couple different ways here. I think what I'm going to do is I'm going to start by writing the dissociation reaction for formic acid first. So I will write that, and I'm going to do it plus water. Remember, for an acid, you don't have to do it plus water. The acid will donate this hydrogen to water. So you're going to end up with the formate ion. And remember that the hydrogen that's associated with the carbon is not the one that's lost. I'm going to set up an ice chart, and then I'm Xing out water because it's a pure liquid. Okay, now I'm going to substitute or include what I know. So I know I've got a 0.10 molar of formic acid. Before formic acid dissociates, there's no formate ion and there's no hydronium ion. Okay, now this one's a little bit different because we have pH. And so from pH, we can calculate the concentration of the hydronium ion. So if you remember what we did several days ago, the hydronium ion concentration is equal to 10 to the negative pH. So if we do 10 to the negative 2.38, we will get 4.17 times 10, that's for you, Sam, to the negative third molar. Okay, now this is the concentration of hydronium ion that is present in the solution. So that's really this right here. So we can fill that in. So I'm going to do that in pink. And I think I'm also going to do it not in scientific notation. So 0.00417. And if I'm doing sig figs, two numbers past the decimal, so I should have 2 sig figs. So let's get it that way so it looks a little bit more normal. Okay, now this is the kind of equilibrium problem where you're given one equilibrium concentration, and then from that you can determine the change. So if we had no hydronium to start and it's now 0.0042, we know that that went up by positive 0.0042. Because hydronium and formate are in a 1-to-1 ratio, formate also increases by 0.0042, and then the opposite side of the fence, formic acid, goes down by 0.0042. So now what we can do is we can determine the concentrations of all of the other species. These are all molarities at equilibrium. So this is 0.0958 molar. Okay, now from this we can calculate Ka. So if we write the expression, Ka is equal to the concentration of the formate ion times the concentration of the hydronium ion divided by the concentration of formic acid. And then we're just going to substitute these values in. So because formate and hydronium are the same, it's going to be 0.0042 squared divided by 0.0958 and we get, let's check out sig figs. We're going to do 2, so 1.8 times 10 to the negative fourth is our Ka. Okay, the next example is the same kind of problem. So if you've got it after that first one, you don't need to watch this one. Okay, so we've got niacin. There's the structure of niacin, and gives us a concentration of niacin. Remember, this is your carboxyl group, so this is an organic acid. They give us a pH, and they want Ka. So the first thing we can do is write a balanced equation. So I'm going to do niacin plus water. Let's do it without water this time so you can see what happens if we do it that way. In equilibrium with the hydrogen ion, which is actually going to be this hydrogen here, plus that same structure, just without the hydrogen. Okay, so I'm going to draw an ice chart, fence under the arrow, and then I'm going to fill in what I know, which is 0.020 molar niacin. Each of these have no concentration to start. Okay, because I've got a pH, from pH, we can calculate the hydrogen ion concentration, and that is 10 to the negative pH. So 10 to the negative 3.26. That will be 5, let's see, 2 numbers past the decimal, so 2 sig figs, 5.5 times 10 to the negative fourth molar. Now that's hydrogen ion, which is this right here. So now we're going to substitute or fill in our table. So this will be 5.5 times 10 to the negative fourth. Now you probably figured out from last time, because these two are in a 1-to-1 molar ratio, that this will also be the same thing. And this will be 0.020 minus 5.5 times 10 to the negative fourth. Now, if you need to see the change to understand that, this is going up by 5.5 times 10 to the negative fourth. This will also go up by 5.5 times 10 to the negative fourth. The opposite side of the fence goes down by 5.5 times 10 to the negative fourth, and that's because they all have a coefficient of 1. So now we want to solve for the Ka. And to do that, I'm going to take the concentration of our products, so 5.5 times 10 to the negative fourth squared. Notice I'm skipping writing the expression here. I'm just doing that to save us a little time. And I'm doing 0.020 minus 5.5 times 10 to the negative fourth. And then I'm going to solve. And I got 2 sig figs, 1.6 times 10 to the negative fifth. Now the question doesn't ask us to do this, but just as a review, if they were to ask what percentage of the acid is ionized, so they're really looking for percent dissociation, remember what you're doing with that is you're taking the hydrogen or hydronium ion concentration and you're dividing it by the concentration, the initial concentration of the acid. So what we would do is take 5.5 times 10 to the negative fourth divided by 0.020, because this here is the initial concentration. Both of these are times 100. And if we do that, we get 2 sig figs, 2.8% ionized.